মহিলারা মিত্র মিত্র
Okay. Okay. So this is the second session of the day 4. Dr. Chandri Chaudhary will give the presentation. Dr. Chandri Chaudhary is an associate professor in the Department of Computer Science and Engineering, Dadapur University. Her research interests include IoT in healthcare, indoor localization, human activity recognition. She was awarded postdoctoral fellowship by Erasmus Mandas in 2014 to carry out the research work at University of UK. She is actively involved in organizing international conferences such as AI MOOC 2015 and 2016, RETIS 2015, several workshops, especially on IoT machine learning. She has also served as a technical program committee members of many international conferences. She has published more than 70 papers in reputed journals and international peer-reviewed conferences. She is a member of the IEEE and IEEE Society. She will speak on smartphone sensing based activity recognition. So I request to Dr. Chandri Chaudhary, please start your presentation.
Thank you so much, sir, and for giving us the opportunity. So without any delay, I would like to share my presentation. Is it visible?
You just mute yourself. Anirban go. You just mute yourself. Anirban go.
Yes, 1 minute.
Dem Kumar. Okay. You just Dr. Chandri.
Okay. So thank you, and a very good afternoon to all the participants. I hope you are safe. And let us start our presentation today. So it is on smartphone sensing based human activity recognition. Okay. So let us start with the very first term, which is smartphone. Smartphone is a very interesting device that we have, and it's not really a phone, but it is doing many different works beyond a phone. For example, it can be viewed as a communication device through which we can communicate through like sending mails, WhatsApp, and so on and so forth. But it can also be viewed as a computation device because it can do a little bit of computation as it already has our own OS which is running, for example, Android OS and so on. And also the one feature which makes it so interesting is sensing capability of the smartphones. The smartphones are coming up with many different kinds of sensors which can sense the ambient conditions, and hence you can have, and since it also has some computation capability, so you can like design applications, design apps that would respond to those ambient conditions. For example, your smartphone has a ambient light sensor which can sense ambient light and accordingly can adjust the brightness of it. It has the gyroscope, the orientation sensors through which you can, it learns the orientation of the device, for example, horizontal orientation or vertical, and turning of the phone and so on and so forth. And accordingly, you can see the screen. And also, all these kinds of sensors, for example, camera can also be viewed as a sensor. If you like take pictures, and if you want some decision to be taken based on those pictures, so there you treat this picture as data, or maybe video as data. So all these kinds of smartphone sensing applications, the applications that involve smartphone and treat smartphone as sensors, all these type of applications have one thing in common, that they are data intensive. A very common structure of them is that you will use that smartphone as a sensor. You will collect data from that smartphone and then send it to some remote server over the internet. And I know that throughout the previous sessions of this workshop, you have already learned about this remote part, the remote servers, the cloud servers, how they are operating, and so on and so forth. So obviously, I will not go into the detail of that, but or rather, I will. Let us focus on this part first, the other part of the internet for the time being. Okay. So smartphones are also equipped with wearable sensors, which actually, helps us to do this, enable us to perform this kind of human activity recognition and its associated applications. Okay. And with respect to the body sensor network, the smartphone is once again one device which is capable of storage and communication capabilities. So it is basically the sync with respect to body sensor network. So that means a smartphone can work as a sensor. It can work as a sensing device. It can work as a sync for another sensor network as well. Okay. Not only that, even your smartphone can be an actuator as well. That means it can sense and it can respond back. So how it is? You know that today smartphones can be used to switch on or off your ACs or TV and so on and so forth, because they come with such near field communication capabilities, the IR capabilities, which is normally used in TV remotes. So with respect to that, they are very useful for actuating as well. So if we take a closer look at the smartphone sensors, then you can see that there are many different kinds of sensors actually, like the microphone you have, through which you can even sense noise. Then you have barometer, you have GPS, cellular network is always there. Then you have accelerometer, gyroscope, and magnetometer. So a combination of this accelerometer, gyroscope, and magnetometer is what makes your smartphone enabled or capable of human activity recognition. So whatever we will be discussing in this session are mostly based on the data that is collected through these three or just these two sensors. Okay. And little bit we will also talk about Wi-Fi and Bluetooth proximity. But the main focus will be on accelerometer and gyroscope sensors. Now, but before going into the detail, first the basic architecture on which this thing is based on. So it is the IoT, the normal IoT architecture, but a very simplified form of it. As you can see, it's a very simplified form of it. It has been shown that you have a things layer, then data is sent to the IoT to the service layer through a gateway. Okay. So it is a very simplified form of the architecture, which was initially like when there were not so much vast number of devices which were sensing and sending data. This architecture was quite capable of serving its purpose. Okay, so you have at the back end, you have this kind of cloud servers which are responsible for not only storing your data, your smartphone sensing data, but also it is capable of computing the different kinds of prediction tasks, data analysis tasks, because as I have already mentioned that most of the smartphone sensing applications are data intensive in nature. So you should have this kind of prediction task or data analysis task which will be going on at the cloud end. Okay, so this is a very simplistic architecture where the data is uploaded actually, and what you get back is control. For example, the service that you wish to know, for the prediction results that you wish to know, like that. Okay. Now, if we talk about, based on this architecture, if we talk about the different kinds of smartphone sensing applications that are available based on IoT, in that case, we will find that they can be categorized into these 4 groups. Okay. One is personal sensing, personal applications, where you actually implement the smartphone sensing application. Somebody has designed this smartphone sensing application for you and you as an individual user only. Okay, so this is known as personal applications. For example, healthcare applications that we have today, like how many miles you have walked or how long you have slept and so on and so forth. So it gives you your your activity. It gives you a hint of that. So this kind of applications are personal applications where you are the application is installed for you as a user. Okay, as an individual user. Then we have group applications. For example, this same application that I was talking about, like your fitness calculator sort of thing, or maybe your diet moderator sort of thing. And now you can expand its reach, okay, beyond one smartphone, and think of making a smart home. So if you make if you think of a smart home sort of IoT application, go beyond one smartphone and think of this, then it becomes a group application, because a smart home application doesn't treat you as the only user, but whoever is staying at that particular environment is a potential user of that same application. So though it is not for a big group of users, but yeah, it is for a small group of users. So that's why this smart home is a kind of application which is not really personal. It is beyond personal, but it is not really a community application. Okay, it is for a group of people. Now, if we once again expand our reach even further, then the third kind of applications that we can think of is community application. For example, crowd sensing or crowdsourcing type of applications are community applications. Yesterday, Professor Sharbani Roy was talking about crowd sensing, and she also demonstrated the different kinds of a range of this crowd sensing application for smart cities. So I will not go into the detail of that, but I will just tell you that this kind of crowd sensing is becoming so popular because you have smartphones which are because smartphones are carried by almost every individual today. For example, we are also having like the Arogyo Setu app, which is used for not only sensing your condition, but also for getting, but also to inform you about your vicinity. right? Awareness application basically. And then the last category is industrial application, where industry, for some industrial purpose, this kind of smartphone sensing can be used, like personalized insurance, where depending on your driving behavior, the insurance company will sense your driving behavior, and then depending on that, like if I have a very rash driving behavior, in that case I will be charged with more premium, because you know that I'll be prone to cause accidents like that. Now if we talk about human activity, I will come to that later. I will come to this slide later with respect to human activity recognition. But first, let us discuss about the technique. Like we have already discussed about the device, that is smartphone, little bit of it. Then we have discussed about the architecture, the big picture architecture that enables us to do this kind of smartphone enabled human activity recognition or any other sensing application. And then we have categorized these different kinds of applications. And finally, the one thing that enables this kind of data processing applications is, of course, machine learning, isn't it? Machine learning techniques are making this data processing things so efficient that you know that today this subject is so popular and it is so effectively used in almost every discipline. And here also, like for smartphone sensing applications, for all these kinds of applications, machine learning plays a very important role. Okay. So let us discuss about the technique, the basic technique, the basic steps that are followed by any sensor data application, not only human activity recognition, but any sensor data application, prediction applications. The basic techniques start with data collection. Okay, so you will collect data. Now you can collect data from the smartphone sensors. You can collect data by, deploying some dedicated sensors in your place, at your place. For example, in smart home applications, it will not be only you will not be using the smartphone sensors only, but you will also have some sensors deployed in the at home at various places for various purposes. Okay, so data collection is one of the first tasks and one of the key tasks. After you have data, what you need to do, this data that you have, that you collect, is generally very noisy. Okay, so you need to pre-process the data. It is not ready for applying any machine learning application. You have to pre-process the data, clean the data. Sometimes you generate some data. For example, you are interpolating or extrapolating things. So there are procedures. You cannot just generate data the way you like, but you have to interpolate or extrapolate or so on, data transformation. So there are different kinds of data processing techniques depending on the application, depending on the sensor data. Okay, so you have to apply those data pre-processing in order to have your data clean from noise and which is ready to be analyzed. Often the data that you get, even after cleaning, it may not show any obvious correlation. For example, whenever very bad example, but still, like if when I am staying in Jadavpur University, the GPS value that my phone shows, if it is same while I am residing at my home, in that case, no machine learning classifier will be able to classify or will be able to learn from this data and classify whether I am at home or I am at Jadavpur University. Because the data, even after cleansing, the data doesn't show any correlation with the label. what is the label? The label is either Jadavpur University or home, so my position. Now, if for both the labels, the sensing data is showing the same value, then yeah, you cannot localize the, or you cannot, even if you apply the classifiers, it will not be able to decide about it. So you have to establish some correlation between the sensing data with its label, right? So for that, feature extraction will help you out. Even if you have some data correlation, then feature extraction will even be able to find out, or rather, yeah, to find out more interesting patterns out of it. See, if both the GPS feeds for my home and Jadavpur University is exactly the same, then obviously with GPS, I will not be able to identify or localize. But it may be that there are some subtle differences which are not so prominent, but there are some subtle differences. So what feature will do, feature will just highlight those subtle differences, or what to say, exaggerate those subtle differences, so that they become not subtle but appreciable. In that case, the machine learning classifier will be able to classify them effectively. Now, not all features are, sometimes you may end up with extracting a huge number of features. In that case, you have to select the important features and discard the redundant ones. So which is feature selection. And finally what you started with is some sensor data or sensor signals, and finally for what the classifier is getting an input is basically the set of selected features. So it's a feature set, from data set to feature set. Okay, and then you finally feed this feature set to the classifier for classification. So this is the overall structure, and you can see that for any sensor data processing application, these are the main steps. Grossly, these are the main steps that are followed. Am I audible?
Yes. You are audible.
Okay. Thank you, sir. Okay. So next, let us move on to, once we know about the architecture, we know about the technique. Now the thing is that, okay, thank you. So now the next thing is where to place these techniques, where to place this machine learning technique. Now you can place the technique anywhere. You can place the technique, the machine learning tools you can install in the smartphone. Who is stopping you from doing that? You can have it. You can have it at the edge devices. Edge was not there in this picture, but the gateway was there. So at this gateway point, we can have some edge servers. I will not go into the detail of edge because you already know about it a lot. So you can place this machine learning tools and techniques at the edge as well. And finally, if you want, yeah, you can keep it at the cloud server. So where to keep it? If you keep it at the cloud server, it becomes cloud learning. If you keep it at the edge server, it becomes edge learning. If you keep it at the device level, it becomes device learning, on device learning. Now, what is the advantage and disadvantage of it? Obviously, storage-wise, if you move, then storage-wise, cloud learning will be the best because you can store a lot many data. And as you know that the primary criteria for machine learning is to have lot of data, to lot of different lot of data that corresponding to different conditions. This is very important. Like if you wish to classify between COVID patient and non-COVID patient with some kind of data, and you only have you have maybe 100 COVID patients data and 50 or 20 non-COVID patients data, then the system will not be able to classify. you have to have significant number of COVID patients data as well as non-COVID patients data. So that means you not only need to have a lot of data, but those data should be pertaining to all the different classes that you wish to classify. Okay. Okay. So obviously, storage-wise, cloud is our best option. Second best option would be to keep it at edge part, and on device would be the last option, because the devices do not have that much of memory or that much of computation power, though they do have some, but that is not significant enough for effective learning speed. Okay, but what you lose if you keep everything on cloud, what you lose is real-time behavior. Why? Because sending this data, if for example, if you're thinking about video processing, then sending this entire data through the wireless connection and then to the cloud, analyzing it over there and getting back the result often incurs significant amount of delay. So real-time behavior is affected when you keep everything on the cloud end. Okay, so for real-time behavior, the best possible option is to go for on-device learning if your data storage or your machine learning classifier actually is not that much sophisticated enough, and if the computation power that is required for the application is supported by the devices, then for real-time tasks, it is best to go for the on-device learning part. Okay. So when to go for edge? When you don't have not so hard build time requirement, or maybe not so vast data storage techniques. It's midway around. No. Edge also has a very unique advantage that at the edge, you know that from which location the device is sending you the data. Isn't it? Because a device will always connect to its nearest edge device, nearest gateway. So automatically you understand from where the device is connecting. So if you wish to apply any location sensitive filtering to the data, if the data requires any location sensitive filtering, that can automatically be done because you know where the edge device is placed. It's not done with the help of the GPS. I'm not talking about that. With the help of the GPS, the cloud will also be able to know from where the device has communicated. I'm not talking about that. I'm only saying that you know where the edge servers are placed. So whenever a device connects to the specific edge server, you immediately know that this is a device from this region only. This is not a device from this region, from any other region. So any location sensitive processing you can automatically do at the edge part. And not only that, any context sensitive processing can also be done at the edge part. With location comes the context, because context is more than location actually. So if you can sense the location, you can also sense the context as well. So, but in case of cloud, this kind of inherent location or context sensitiveness is lost. Okay, so edge gives you this advantage, but it comes with a disadvantage as well. What is the disadvantage? The disadvantage is that obviously a device can move from one region to the other. So let's say it was processing some data, it was applying some learning technique, and while it is not completed, the device may have moved from here to some other part. So in that case, what will happen? What this edge server will do? Will Will it send all its half computed results to the next stage server or like that? What will happen? So this kind of strategies or distributed kind of computation model for machine learning, though these are the research challenges that you have for age learning, and it is only at a very initial stage. As you can see that this part is taken from this paper which is published in January 2020 only. So age learning has only begun, and people have started to realize the potential of putting this machine learning techniques at the age. So you had some scope of work on it, and for most of the works that we will be discussing about in this session is definitely incorporating the learning algorithms placed in the cloud. Even if it is not a cloud server, it is a standalone server, but yeah, it is of course that you have to reach there through the over the internet. Okay, so these kind of human activity or any sensor data application you can execute on your device only if it has internet connection ongoing. If you wish to enjoy its benefit even when you do not have internet connection, then yeah, your device must be powerful enough to execute this kind of on-device learning part. Otherwise, it won't be, right? So this was the comparison. Now we have already talked about the big picture, the architecture, the technique, and where to keep what. Now let us dive into the particular application that we have planned to discuss in this session, right? So that is basically human activity recognition. Yeah, but we will start with smart healthcare, where human activity recognition comes as a inherent part of smart healthcare applications. So why this kind of health, why you are with smartphone, we are talking about this kind of health, smart health, and so on and so forth. You see, because you can say that whenever if I get fever, then I will ask for medicine. If I get cold and cough, then I will, go to the doctor or something like that. If I feel any symptom, then I will go to the doctor and I will have medicines. Then why you are talking about health, smart care, and so on and so forth. So it is because there are several studies actually which indicate that in India, 60% deaths are caused by not any communicable disease, but due to some chronic diseases, which are non-communicable but chronic diseases. Okay, so these kind of chronic diseases have a common pattern, and the common pattern is that you feel you are fit, you don't feel any symptom, and when you actually feel symptom, it is quite late. And the only way to treat this kind of diseases is to prevent them from happening. And how can you prevent them? Even when you are not feeling any symptom, still what you will do, still you have to go for this kind of monitoring vital signals such as the heart rate and something like that whenever the patients are engaged in normal activities. Okay, so this kind of daily monitoring will help you to keep you to prevent you from this kind of chronic diseases from happening. And actually there are like the medical science has progressed a lot, and so if they can identify the chronic diseases at a very early stage, then yeah, it can also be prevented. So this is a typical picture of a wireless body area network where the smartphone is acting as a body area network aggregator or a sink, you can say. there are different kinds of sensors which are attached to the patient's body, and they form a sensor network, and then the data that is generated by these different kinds of sensors will be aggregated at the sink, which is the smartphone over here, which can be like, you can have any other dedicated sync device, but smartphone can also work as an aggregator. That's what I'm talking about. So this smartphone then can send this kind of aggregated sensed signals from all these devices through the internet to the caregiver or physician. So what is the advantage of having this kind of information propagation path? It is that now the patients need less hospitalization. In a smart health environment, this can be done, right? So while staying at home, while enjoying the autonomy at home, the patients can be monitored, and doctors can see their levels, their different body vital levels, and accordingly they can assist or treat the patients effectively. Like sometimes it happens that whenever a patient is going to a doctor, is visiting a doctor, and the doctor is doing the ECG monitoring, the patient is so nervous, so tensed that the exact monitoring is not happening. Something abnormal is coming out, not because he has some problem, but it is only a momentary stress. So that kind of things will not happen when you monitor for 24 hours while the patient is at home and he is enjoying his normal daily lifestyle. Okay, and also like it is pocket friendly because you don't need the hospitalization charge, and these sensors are not that much. Typically, they are not that much expensive. Actually, this kind of solution will work only when the cost of this kind of solution is less than the hospitalization cost or plus the cost of caregivers. So works are going on in this direction as well. So I was talking about this, the non-communicable diseases and the communicable diseases. Though currently we are all suffering from this problem of highly communicable disease, but hopefully it will be solved. And so what we were fighting against was primarily non-communicable disease, and this kind of so this kind of system not only can help us to monitor for non-communicable, but yeah, for COVID patients also you can monitor these body vitals like SpO2. People are saying that you get a device at home and check for your own oxygen saturation levels and so on. So you can see that this kind of proactive monitoring, that's what is talked about in smart healthcare, is so much demanded by our society right now. Okay, and this is a graph that shows the healthcare expenses, average expenditure per hospitalization in rural, urban areas, and the GDP per capita. So as you can see that when we are earning more, the rate at which we are earning more day by day is less than the rate at which we are spending for our healthcare costs. Okay, our healthcare costs are increasing at a rate which is beyond the rate we are earning. Your salaries will be increased, but your healthcare expense will increase more than that. That's why we need to think of this kind of solutions to curb our healthcare cost. And this is not only the scenario in India, but this scenario is common in almost anywhere in the world, even in the developed countries. So proactive wellness management is an issue, and early detection and prevention is the only key through which you can lead a healthy lifestyle. That's why there are several government initiatives as well. The government is spending a lot of money, and you can see that there are certain camps which go on for blood tests and so on. Then many different initiatives are taken out, not only by the central government, but also by the state governments as well, like eye checkup, then blood sugar test, and so on and so forth. So these are all basically this kind of proactive wellness management initiatives. And if you go for this kind of smart health and the activity recognition applications, the way we are talking about this, this is our initiative, the citizens' initiative to remain safe for themselves. Okay. So given this background of smart healthcare, now let us dive into the exact topic of human activity recognition. So what is human activity recognition? Yeah. So human, this is the very definition of human activity recognition. But roughly speaking, if we say what is human activity recognition, then it talks about something like you have an app and you just play that app, and it runs in the background for the entire day. And then end of the day, it says that you haven't walked enough or 5,000 steps a day or something like that. Or maybe you sat for long hours. Or maybe if an elderly person is using that app and if he feels unconscious, then the app can alert it's keen or his keen or his son who is or daughter who is working at office, the smartphone can send a notification that for a long time the person is sitting and there is no change, or maybe for a long time the person is on floor and there is no response, like that. So you see, it can even save lives like that, because as you know that in Kolkata or any urban cities of India, many elderly persons are living on their own. They don't have anyone to take care of them. Anyone means any young adult with them, any adult person with them to take care of them. So that's why like this kind of app is very crucial. Then AGS systems provide this kind of context-aware feedback that I was talking about, that the person fell down somehow or maybe the person was left unconscious for a long period of time, so it can alert. So it is, and also there are benefits like, if he has some difficulty from sitting to stand, or maybe after surgery, some kind of surgery happened and he is prohibited from doing some activity, but he is actually doing that activity. So your smartphone accelerometer can detect that this activity is done, which is prohibited by them. So it can alert, okay, that see, your patient is doing this kind of activity, okay. So for elder care and for smart healthcare, it is human activity recognition is a basic component, and it is an indispensable component actually. Then for daily activity, and then we will also discuss about the other applications of activity recognition. But if we go deeper and see that what we mean by activity or daily activity that we are focusing on, for example, sit, stand, walk. If you look at one activity, for example, the speed at which you climb stairs while going to watch a movie, probably we have almost forgotten how it feels to go to a cinema hall and watch a movie. But anyway, let's imagine that we are going to, you are maybe you have bunked your class. You should not do that actually. Or maybe after your university classes are over, you are going to watch a movie. So the speed at which you are climbing down the stairs will be, I think, much faster than the way you will climb down the stairs during your exam, right? So you see, it depends on the psychological state the physiological state as well. For example, the speed at which we climb stairs from ground floor to first floor is much more than the speed at which we climb stairs from maybe third floor to fourth floor or fourth floor to fifth floor, like that. So it not only depends on the psychological thing, it also depends on the physiological condition, anatomical condition as well. So there are different kinds of effects that are actually deciding about the pattern of our daily activity, and hence the accelerometer traces that are generated for one activity will vary depending on where you are carrying out this activity or when you are carrying out this activity. Okay. Now, beyond this, so that I was talking about, till now we have only talked about smart healthcare and human activity recognition as an indispensable part of smart healthcare. But there are scopes beyond smart healthcare, elder care to be specific, or smart home to be specific. For example, in sports, you have a very interesting application of human activity recognition, like to check the fitness of the athletes, to check whether a footballer is actually physically fit to play a 90-minute game, whether his heart rate, his blood oxygen saturation, and all those things. With analyzing all those details after he plays a 90-minute game, you can understand what he is capable of, or what level of physical exertion he is actually capable of. So this kind of things, then the posture at which the bowling is done, or many different kinds of things you are more aware of. So for those fitness tracking, this human activity recognition is an indispensable part. Like I know about startup company where a very nation, then you can sense that something forcibly is happening to that person, and you can, and if his or her GPS is on, then you can understand and alert others so that others can help that particular person. And also, like, CCTV cameras do not work in the dark, right? So in that case also, like, human activity recognition can be used for surveillance, as a surveillance tool. The next application of human activity recognition is gesture recognition. Gesture recognition, you already know, for example, how to operate, and then depending on the gesture, you can understand what he or she is trying to say communicate to the screen reader, like that. So gesture recognition is also another interesting application, but obviously for gesture recognition, one thing I must say, that, okay, what I was talking about. Yeah. It is not. It is very, very difficult to do with smartphone. You have to have. It is better to be done with wearable accelerometers when you wear the around your wrists, like that. Okay. So these are the broad scale application categories for HAR, and if you remember the classification, then smart healthcare is applicable for both personal application and group applications, but surveillance is surveillance can be used for community as well as industrial application, right? Okay. Now, apart from smartphone, what are the different devices, or what are the exact sensors that allow you to do this kind of human activity recognition? So you have some wearable body sensor that I was also talking about, that you have a wearable accelerometer which you have to wear around the wrist, or maybe you can have SpO2 sensor. Like now people are talking about you should buy some SpO2 sensor and check for the oxygen level yourself. So this kind of sensors are usually worn around your finger. Then you can have like this particular device. It looks like it probably looks familiar to you, and many of you may have this kind of device, which actually has accelerometer and gyroscope, this kind of sensors embedded in it. Okay. Then heart rate sensors are also available. Heart rate sensors are not necessarily, worn around the chest always. One of my PhD students once came up with a heart rate sensor, which is not very expensive. That's why she was like we were able to procure, and she did once. So now you can actually group, depending on what kind of sensor is used for activity recognition, you can group the works into these different categories. One is variable sensor based activity recognition, ambient sensor based activity recognition, and ambient plus variable sensor based activity recognition. Now, in this session, we will be talking about smartphone based activity recognition and smartphone and wearable body sensor based, and little bit of ambient sensor based crowd behavior recognition. Okay. So this is the big picture of it. I'll not go into the details of this, but let us start with the machine learning techniques and the activity recognition using machine learning techniques. Okay. So why machine learning? The very first question should be, why machine learning? When we apply machine learning, when the problem is too complex and you cannot have a handwritten rule or you cannot have an equation for it, then we go for machine learning. Machine learning is not magic. It's not a magic box that you will put something and somehow it will solve your problem and give you the output. No, it is basically some kind of computing that we cannot think of because it is too complicated, and also because it is too complicated, so we cannot formulate that function at hand using the data that we have. And the second thing is that the second interesting point about machine learning is that it needs to adapt with changing data. As the data pattern changes, it should be updated. It should use some online learning technique to update itself. With the traditional statistical techniques that we already have, probably I cannot, but a trained statistician can be able to develop a complex nonlinear relationship between the data much better than what is very difficult in traditional, even with traditional statistical techniques, is this kind of adaptive nature and this kind of scaling of data, scaling of the solution. So for this kind of dynamic behavior, machine learning works really well, and that's why it is used so effectively in almost every discipline of prediction analysis. Okay, so HAR can be done in two ways, as I've already mentioned. That video, that using CCTV camera, CCTV footage, you can understand the activities of a person quite well. But the problem is that it is very, very pervasive, and the advantage of it is that you are not, it is contactless. CCTV footage like that, video based activity recognition, the advantage that the user is not carrying anything. But once again, it is the disadvantage. Why? Because you have to have a CCTV camera installed at your home. So you have to have a dedicated device. You have to buy a dedicated device at that particular environment where you need activity recognition. But in case of this contactful sensing application, or particularly smartphone based HAR, the main advantage is that you just need to install an app, and that's it. You don't have to install any, you don't have to buy any dedicated device for it. So there comes the pervasive nature of it. Okay, there comes the pervasive nature of it, and that's why you can install it anywhere, and the reach of a sensor-based or smartphone-based human activity recognition is far beyond the reach footage-based or video-based human activity recognition. Okay. The third advantage is, of course, user privacy. You cannot install this kind of video-based recognition systems anywhere, but because user privacy is a to get fine-grained data. So what happened? They start, if when you click on start, for example, here you keep the phone in your pocket, but before keeping the phone in your pocket, you will click on the start button, and then you will put the phone in your pocket. And then, for example, we want walk data. So what you will do after clicking on start and putting the phone in your maybe right hand pocket, you start walking. Okay, you start maybe 2 seconds, maybe 5 seconds, like that. So somebody else has to, you can monitor, but it is better whenever you are taking data for training sets, it is better to have precise levels. So it is better to have somebody accompanying you who will actually monitor your walking and will check the timer. Okay, and let's say after 5 seconds the accompanying person is asking you to stop, so you will take out your smartphone from your pocket and then click on the stop button. So when you click on the stop button, you will see these kind of results, that are this kind of accelerometer data along with the timestamp will be shown. If you use any like normal accelerometer, gyroscope data collection apps that are available at Google Play Store, there also some button which will enable you to start your accelerometer readings, and then you will put your phone in your pocket, or maybe you will hold it at hand, and then you will walk, jump, sit, stand, whatever activity you wish to measure. You will do that for a pre-specified amount of time, and then you will click on the stop button, and you can see the readings that are coming up. So when you click on the stop button, actually you can upload this kind of data in a file as a CSV file to your Google Drive or so. Actually, most of the apps are allowing us to store this kind of readings in a Google Drive. So as you can see that if we were to collect the data for walk, the first few instances are not for walk data. Why? Because start and then putting the phone in your pocket. So while your phone was moved, it was not because of your body movement, it was only for your hand movement. So those are the noisy data that you cannot, use for the analysis. Okay, so you have to filter out those data. Anyway, we will talk about that later. So the essence from it is that whenever you have, let's say, 5 seconds of data, all these 5 seconds of accelerometer instances cannot be used for data analysis. The very first few and the last few instances has to be removed. Only the middle part can be used for data analysis. So typically your HER raw data set looks like that. You will have some timestamp, AX, AY, AZ, and sometimes I will talk about this dimension later, but some sensors, yeah, they allow, then it becomes, very difficult for the analysis. You will have erroneous result. Your accuracy will not be very good because the classifier is not getting a proper data set. Okay, so you will label this data. For example, this data was for brisk walk, so you label it as brisk walk. It is I know it is a very time consuming and a very tedious process, this kind of data labeling and data collection. But yeah, for actually for any machine learning task, data collection and data labeling is the most tedious one. And so we have to do it. One thing you can do is you can also, like, while the person is collecting the data, you can also while the person is carrying the device, switching it on and walking, in that case you can switch on a video and see and measure the timestamps over there, so that you can play the video and play the video, see the corresponding timestamps of the accelerometer, and check whether the person was actually walking, was actually doing something. So that will once again help you to validate your ground truth even further, because it is very important to have a data set having precise level values. Okay. Now, if we plot this this data that we have collected, if we plot this data, for example, here data is plotted, not the entire data, but for each activity, say around 120 seconds of data is plotted. For example, sit on floor is the activity. So while the person clicked on start, kept the phone in his or her pocket, and then sat on floor for some time, which is typically more than 120 seconds, maybe 140 seconds, 150 seconds, and then he or she has, clicked on the stop button and got the data for processing, like that. So we have plotted 120 seconds data for each of these activities. Here you see sit on floor, sit on chair, lying left, lying right, and so on, up to climbing upstairs and climbing downstairs. These data are very tedious to collect, because while you are climbing stairs, if you have climbed 10 stairs, then only the activity of climbing 8 stairs could be used. The first stair and the last stair cannot be used because those are erroneous data. And in that case, if you take those data into consideration, then the system will be confused with walk or brisk walk, like that. So you have to remove those data and only get the middle part, that is maybe the climbing, the 8 steps, middle 8 steps will be used for analysis, like that. So collecting training data, after that, this is the kind of pattern that you can get. Now, can I, sir, can I ask small questions to the participant in order to just, just have some kind of interaction with them?
Okay.
Okay, so thank you, sir. So my small question, just to make it a bit interactive, just by looking at this picture, can you tell me that whether we need because you know that these are the reasons when we go for machine learning techniques, and these are the reasons when we go for machine learning techniques. So if I wish to classify between what are static activities and what are dynamic activities, I'm not saying about sit on floor, whether you can detect sit on floor. I'm saying that if you can detect about static activity versus dynamic activity, then do you really need machine learning technique? Or how can you detect that? Looking at this particular plot. Uh-huh. Okay, how many of you think that, yeah? Yes, anyone? Okay, how many of you think that yes, we need machine learning technique to, yeah, yeah, yeah. So how many of you, have anybody responded? Okay, okay. Okay, fine, fine. So is there any question till now? Is there any question till now? Then you can post your questions also. Okay. Please feel free to interact and please feel free to post your questions as well on the chat box. Okay. So see, by looking at this graph, you immediately understand what are the for example, the yeah, was there anything? Yes, Momita. Email will be required to differentiate between two static and two dynamic activities. Yeah, very good. Very good. Thank you, Momita. So what I was talking about, yes, by looking at this figure, you can immediately understand that the left part of the figure constitutes of static activities and the right part of the figure constitutes dynamic activities, right? Just by looking at this graph. So how can you basically understand that? You see the standard deviation or the variance in the at the right side of the graph is much more, but the standard deviation or variance at the left side of the graph is much less. So if you write a program if else that standard deviation more than something, then it's dynamic activity, less than something, then it's static activity. But if you distinguish between two static activities like sit from lying left, like sit, this blue red from lying left, this orange and purple, probably, I don't know. So from the first two to between the difference between the first two and the third and fourth, in that case, yeah, it is not that much apparent from the raw data plot. And so, as Momita has already pointed out, we do need machine learning technique to distinguish between such static activities or two dynamic activities. But just to know whether one static activity, whether it is a static or it is a dynamic activity, you don't need any machine learning algorithm. You can straight away write a if else conditional statement and you can do it. Okay. But the problem is not so simple. I have already talked about this annotation scarcity part. I will not go into the detail of it, but I will go into the detail of this. The problem is that the kind of activity pattern that you are getting in this plots, it is for one user only. Now, if you plot the activity user, you will see that the pattern changes. Same activity, even if she or he was collecting the data with the same device, then also the pattern will change. For example, the speed at which you normally walk will be different from the speed at which I will normally walk, isn't it? So since I am older than you, typically, so obviously your normal walking speed is more than my normal walking speed, and hence this kind of plot for you will be different from me. So likewise, for different users, for example, the athletes who are very fit otherwise, so for them the normal walking speed is almost probably probably more than my brisk walking speed, like that. So the pattern changes with users, then the pattern changes with time as well, as I have already mentioned about it, and finally the pattern changes with sensors. So let's see how the pattern changes with sensors. When you have raw data from two different devices, let's say the same process we have carried out for data collection, and we had and we have kept the device, two different devices, and for the same kind of activity we have we have the data. So you can see that these are the plots for two devices, and as you can see that for this part, particularly for brisk walk, you can see a visibly different brisk walk pattern for the different, due to the different devices, even when the data were taken by one individual only. So the user was same, only the device was different, and you see the plots for the same activity was different. Similar thing happens with smartphone usage behavior as well. We don't keep our smartphone always in right hand pocket. We can keep it in our bag. We can keep it in our shirt pocket. We can hold it in our hand. Obviously, if you put it in your table, then we don't have anything to do with activity recognition. You have to hold the phone, or it has to have some body contact in order to sense the acceleration. So if you have so depending on where you have kept or how you are carrying the phone, the plot for the same activity varies. Like here you see the plot for brisk walk varies depending on how you are carrying the phone. Okay, so this kind of device problem due to device heterogeneity due to device configuration and smartphone usage behavior is not present if you perform human activity recognition Fitbit, because you know where to attach the device, or maybe smartwatch, because you already have a dedicated device. So the concept of different devices with one software, one learning is not there. Whenever you are getting the data, you know that it is coming from that device only. And also for smartwatch, this kind of usage behavior difference is also not there. So these two challenges are unique for smartphone based human activity recognition. But once again, the advantage for smartphone based human activity recognition is that you are not purchasing a new device solely for this purpose. Okay. But as I was telling you a number of times, that this data collection is a bit tedious, and this kind of labeling data minutely by looking at the patterns, these are a bit tedious. But to help you out to start, if you wish to start working on this topic, there are many data sets, accelerometer data sets, which are already provided, accelerometer gyroscope data sets. The UCI machine learning repository gives you this kind of UCI HAR data set. You see many UCI data sets are there. Then this PAMAP2, this data set can also be used for the classification. I have so many data sets which are handy, and you can get a list. This list is actually taken from this particular survey. So you can get actually if you visit UCI machine learning repository, you can get this kind of opportunity data set. So these are the data sets which are normally used for activity recognition, benchmark data sets. Okay. So once you have enough data, then the next thing is, of course, to go for data pre-processing. Now, in case of data pre-processing, the first thing you need to do is you need to clean the data. So how you can clean the data? You can clean it by, removing its spikes. And not only that, the accelerometer contains some components, some gravity components, which are the low frequency components, which are not the linear acceleration component. Filter out the gravity component so that only the linear acceleration is better for analysis. But sometimes, you may need the gravity component as well. So that depends on the type of activity that you wish to perform. For example, for climbing upstairs, downstairs, or maybe sitting on floor or sitting on chair, you need this kind of other components which will help you to understand. Okay. And data normalization is in data normalization, what happens? You scale the data between 0 to 1 range, but also you lose some of the information, like this curve is much flat than this curve, and you lose out this kind of variation part. So it totally depends on the application whether you would wish to apply data normalization or not. Now, the effect of usage behavior is shown here in detail. Okay. These plots where, if you look at it, this is something like +4 or 6, +6 point something, and this is -6 point something. This is +1.2, this is -1.5 or so, like that. Because this data was taken by just flipping the smartphone upside down. So the data was taken for lying left and lying right. These two activities, lying left and no, only one activity, lying left. And so while you are lying left, you have kept your phone in your right hand pocket only. But the thing is that only difference is that for the first time you have kept your phone straight away, upside down, straight away, and the next time you have flipped the phone upside down and kept in your pocket. Okay, so though the position was same, but since the orientation of the phone got changed, so you see the direction got changed. But why I'm talking about it is that the two postures, lying left and lying right, will have almost similar linear acceleration values. The only difference is in their direction. But if you flip the smartphone in the opposite direction, then what will happen? Lying to, for that you have this Z direction, this gravity that was mainly doing the mainly sensing the gravity part, but it is also insensitive to towards this kind of flipping because it is the vertical axis. So in that case, with the by considering the Z component and adding a new dimension, which is the magnitude of the value, sum of the square of magnitude of these three acceleration values, by adding this new dimension, you can actually figure out this difference, or you can actually, what can I say? You can actually remove this kind of difference, because you don't want your analysis to be different when your phone is upside down. You can't ask the user to keep your phone in your pocket in a straightforward manner and don't flip it. In that case, my activity recognition app will not work. You cannot say that. So your data processing technique should be smart enough to cover this kind of problems. And that's why you can add this new dimension, which is √ax² plus ay² plus az², which says the signal vector magnitude. Okay, so once this is done, the next part is, of course, feature extraction and selection. But before doing it, can I take a break and see if you have any questions? Do you have any questions till now?
Participant, do you have any question?
Okay, Kunal. It is clear till now. So I hope you are all listening. Actually, yeah. So I hope you are all listening. So the next part I will move on to is feature extraction. In case of feature extraction, what we do is that you typically group the features, okay? You group the features into some segments. For example, the first 2 seconds, whatever accelerometer instances were collected, you group it into one row, and then you call it one segment, okay, and like that. So it's something like let's say we have a list of features. Yeah, we have a list of features, and let's say we have a group. We will group 3 instances together into one segment. So 1, 2, 3 will be grouped into segment 1. Okay, so 1, 2, 3 will be grouped into segment 1, but actually it is not like that. And then 3, 4, 5 will be grouped into segment 2. It is not like that. So what will happen? We will group 1, 2, 3 to 1, segment 1, but 2, 3, 4 to segment 2. Okay, then 3, 4, 5 to segment 3, like that. So that means you will group these things, you will group your data into segments in a following the sliding window pattern. The window will slide, and normally 50% overlap is done. That's why I was saying that 1, 2, 3 is grouped into one segment, 2, 3, 4 is grouped into the second segment. Okay, so this kind, and after, why we are doing this kind of segmentation? So that you can extract meaningful patterns from it, you can extract features from it. For example, you can take an average of the first 3 instances, which is the mean feature for segment 1. Then similarly you can extract mean feature for segment 2, and so on. You can calculate standard deviation of it. So likewise you can calculate the time, many time domain features, and not only that, frequency domain features also you can calculate. For example, you can change this kind of signal representation to its frequency domain part, and then from the spectrum you can take out maybe FFT mean and so on and so forth. Okay, so this is the way we take features, and like you can have you can group 100 of features, 100 of instances together as one segment. You can have 50 instances together for one segment, like that. So how many segments to group together, that would depend on the kind of activity that wish to perform and the sensor that you are using. For example, for accelerometer, normally 1 second, 2 seconds, this kind, or 5 seconds, 30 seconds, even hundreds of seconds windows are used. For heart rate sensor, typically 30-second windows are used, like that. Okay, and these are the normal features that we generally use for human activity recognition. Now, what are the problems? I think I have already talked about these problems, like it is difficult to distinguish between 2 static or 2 dynamic activities for which you really need this kind of feature extraction. And another challenge for feature and also, like, some dynamic activities are very difficult to distinguish between, even if you have features such as standard deviation, variance, etc., because they can give you similar values for normal walk and brisk walk. So to distinguish between them based on these features is very difficult. And also, so this leads to the interactivity similarity, that 2 different activities, but the accelerometer pattern or the features extracted from the accelerometer patterns are similar. So those are the problems that we should take into account. So if we talk about this figure, I hope you remember this figure. For these are the different performance accuracy actually plots for different feature subsets. And as you can see, that as the frequency domain features were introduced in feature subset 3 and 4, the overall accuracy for the different activities actually increased a lot. Particularly for the dynamic activities, the performance is improved when you have introduced a new kind of frequency domain features. And this is its corresponding confusion matrix. Okay. I hope you know the structure of a confusion matrix and the accuracy definition of accuracy. So can I assume that you know about it? Yeah. Okay. Okay. So the next thing is, let us go for the what else we can do with this kind of activity recognition. So we can add feature fusion, like fusion from different sensors, or we can go for ensemble of classifiers. Okay, so when to go for, so I will take an example of both. Okay, so the first thing is feature fusion. So while talking about feature fusion, like this is the kind of physical level exertion that you go on while you are walking and carrying a weight. For example, carrying your laptop bag and you are walking, then the kind of physical level exertion will be more than when you are walking but you are carrying nothing. You are not carrying any weight, but since your acceleration pattern will be same, body acceleration or linear acceleration will be similar for both the activities. That's why it will not be, but that's why your machine learning classifiers will not be able to recognize this kind or distinguish between these kind of activities like running and running with weight, or maybe walking and walking with walking. So for that, this kind of feature fusion techniques can be very handy, where you have different sensing modalities and then you will have one feature set having features extracted from the different sensing modalities. Obviously, the different sensors will have I was talking about segmentation. So ultimately, using interpolation or extrapolation, all those techniques, you have to have a unified segment length. Okay. For example, it can be 30 seconds for both heart rate and accelerometer if you are using a combination of them for activity recognition. And then this one feature set will be used for will be fed to the classifier for selection. So this is an example that we have the experiments that we have conducted for this kind of using smartphone acceleration and the variable heart rate combination of classifiers. Combination of sensors. And this is the result that you typically get while you are trying to classify this kind of intensive activities only using the accelerometer. But your detection performance will definitely increase when you incorporate features from both heart rate and accelerometer. So you can see that that this kind of activities like say 3 and 4, walking and walking with weight. So walking and walking with weight, they had like 78% and only 47% accuracy, but now they have 96% and 93.56% accuracy. So you see the accuracies have classification accuracies have improved a lot with this kind of by incorporating this combination of heart rate sensor along with smartphone accelerometer. So this is one way, feature fusion. The other way is to have an ensemble of classifiers. Now the ensemble, in case of an ensemble of classifiers, what we do is that, for example, here the different sensing modalities are treated as one classification model. But for example, I will talk about one particular example where this kind of different training sets were taken, and like this training set is formed using device 1 when it was carried at position 1. Then this particular training set was taken using the same device, but the phone was carried at a different position. For example, let's say P1 is right pant pocket and P2 is shirt pocket, P3 is hand, like that. So different training sets you have a number of training sets corresponding to the device you have used and the position where you have kept your phone for data collection. Now, for each of these training sets, we build a classifier. Okay, so we have a base classifier which is tuned differently. Definitely it will be tuned differently now. Let's say we have KNN. If we have KNN classifier, then KNN will be tuned for some value of K for this training set. For this training set, it will have a different value, and so on and so forth. So you have tuned your classifier parameter tuning for these different training sets, and so this classifier plus the training set, this kind of tuning is giving you K number of classification models. Okay, now once you have this K number of classification models, so this here ends the training part. Now, when a test data is captured where you don't know what was the training device and how the training device was kept, the training device can be even a totally unknown device, which is not, whose data is not present in the training set. Still, your system should be able to identify now, because you are applying machine learning technique and you are claiming that it is adaptable. So whenever this test data comes for possible classification, then what it is doing, this test data will be classified by each of these classifiers, and then there will be a majority voting between their prediction outcomes. Okay, for example, for one instance, classifier 1 has predicted that instance to be sit, classifier 2 has predicted that instance to be stand, like that. So you will perform typically a majority voting of them to understand what is the actual activity, or what is your decision, what is the ensemble's decision, that whether it is a sit or a stand or whatever it is. Okay, so this kind of condition based ensemble classifier can be used for activity recognition, and using this, you see, these are the results that we found. So you can see that ensemble actually performed much better, even when you, here we had here D1 was the device, and D1 device's training data was also present, and D1 was the device was carried in short band pocket for the training as well as for the test. So here the ensemble accuracy is 91%. But let us take this example, this example where D4 is a new device and D4 device's data is not present in the training set, and still the ensemble is able to classify the activities with 79% accuracy. And if we take this particular, how the device is carried by the individual is also not known to us. So even when you have this, you have a new device and the device is carried in some way which is not represented by any of the training sets, still the system, because it is performing a majority voting between the things, between the base classifiers, it is able to identify the activities with 78% accuracy. So these results were taken particularly for using only smartphone accelerometer. Now, if you add gyroscope sensor as well, in a manner I have shown you previously, feature fusion. So if you are doing feature fusion and then ensemble, okay, then you can see that in the previous set, it was 78%, and now it is 80%. Here it is 81%. So the accuracies are actually improving. If you add gyroscope, because gyroscope allows you to effectively classify activities like climbing upstairs and climbing downstairs. For those activities, accelerometer will not be of much help. Okay, so till now, it was about activity recognition using ensemble. Using machine learning techniques. I hope it is clear to all of you. And so I will move on to deep learning in HAR. Okay, so what is the motivation for it? As I have already mentioned that even, for example, in this particular case, you see, even now also, the last two activities were for standing and standing with weight. And standing with weight, we are not having, much improvement, right? It is 82 to 84%, 89 to 91%. So to distinguish between such things, you see that adding a new sensor is not always it is not the ultimate solution, but we need something better than that. So what is it? Till now, there is no such clear way of extracting features. You don't know which feature will work and which feature will be, will just confuse maybe. So the feature engineering was, or feature extraction was most likely be done by the experts having some domain knowledge probably about the system. And also features are basically heuristic in nature, but there are no universal or systematic way to extract features. But some features are there which we cannot, for example, if I say that you, by looking at a picture, you immediately understand that this is Shunirmal sir's picture and not Devashish sir's picture. So how do you know that? Now, if I ask you, how do you know that, which feature you look for, then you will think that how I have done that. So it is sometimes our brain thinks in a way which is very difficult to formulate or quantify, So while you are trying to, help your machine to understand the kind of features, it is very difficult for us to actually formulate or quantify that particular thing that we feel, but we can't, define it. So for those kind of things, deep learning is a very good alternative. Why? Because it automatically extracts the features. And so it will also extract those high level features, those non-complex relationships it will capture in the feature very easily, which is very difficult for you to formulate. And what are the advantages of deep learning? The first advantage of deep learning is that its layer by layer structure is detachable. So you can, you can add layers, you can remove layers and so on. And also they can learn as you add new layers, they can learn from simple features to abstract features in a scalable manner. Okay. So that's why this is very important. And normally in activity recognition, you can see a lot many literature on CNN which talks about video-based human activity recognition. You can find that, or image-based. I'm sorry, video, I don't know, but image-based things. You will find literature, very rich literature on CNN and how CNN works on that. But for this kind of activity recognition, which talks about time series signal, probably it's not that much saturated a field till now. So CNN is generally used for activity recognition, sensor-based activity recognition, in order to study the relationship between different modes of data. For example, okay, I will show you in detail shortly. And you have the other option for deep learning models, which is RNN, recurrent neural network, then long short-term memory, LSTM. So for all these kinds of, which is basically a kind of RNN probably. So this kind of structures, deep learning structures, they enable you to extract temporal dependencies between data. And so for streaming sensory data, in case of for real-time human activity recognition, if you have obviously a good communication speed and some cloud service running over the internet and so on, and no problem with bandwidth, then obviously for real-time human activity recognition, you can go for RNN or LSTM-based structures, because they are very helpful in analyzing the temporal dependencies between data. Okay. So I will talk about this multimodal CNN, but I'll not talk about this RNN part. I think I don't have much time left also. So let us talk about this multimodal CNN. Yeah. So you have raw signals, which are in time domain, which are typically captured, and we have talked a lot about it. So after that, what they are doing, I'm discussing about one work, which is this work. This is a very interesting work that I found out, which uses convolution neural network to for human activity recognition. And what they are doing is that for some sample, windowing time, that is, I was talking about that segment 1, segment 2. So that sample interval or window interval, they are collecting the data and then they convert that data. For example, they convert the data for segment 1 into its frequency representation. Okay, but before that also they do some processing, but roughly speaking it is something like that. They take the data. Once you are given with data, say you have given with 5 minutes data, and you are dividing it into 10 seconds chunk. So the first 10 seconds chunk you get, now you convert it to its frequency domain representation. And then that frequency domain, the spectral image that you are getting, so once you have the spectral image, you can feed it to a 2-dimensional CNN because you have an image and you feed it there. So what is the 2 dimension? You were fed with 1 dimension, time, 100 seconds I was talking about. But now you have added another dimension, which is frequency, because you are converted to its spectral image form. And now this data you have kept into you are feeding to a 2D CNN, and what this 2D CNN will give you, what a neural network gives as output, it gives you some probability that with this probability, this level is true. With this probability, this level is true. So the DCNN, this will give you an output, 2D CNN, sorry, it will give you an output of probability distribution over the all possible activity classes. So let's see this work in detail. So, so they have taken both accelerometer and gyroscope data, and also they have taken the linear acceleration part separately, as I was talking about the filtered part and the linear acceleration part. So they have taken all these, dimensions. Okay, so that means these 6 dimensions they already collected, and these 3 feature dimensions they have, computed. Yeah. Now the essence of, or the idea behind doing this kind of signal image thing is that there can be a relationship between the data you get in x-axis for gyroscope and the data you get in x-axis for accelerometer. There can be a relationship between, a correlation between the data you are getting along y-axis of accelerometer and the z-axis of accelerometer. While you were doing the time domain analysis, as I have pointed out till now, what we have done, we have collected this data, then for x-axis of maybe accelerometer, we have done the mean, the average calculation for first 10 seconds, next 10 seconds in a sliding window manner. So that means you wish to know the correlation between what was x-axis accelerometer value at some point of time and what was the x-axis accelerometer value at a later point of time. Using this relationship, you wanted your classifier to classify. But now they are saying that this is not enough. there can be some relationship between the x-axis gyroscope value with the x-axis accelerometer value, or maybe the y-axis accelerometer value with the z-axis accelerometer value. So what they are doing is that using basically a permutation combination, some kind of that, what they are doing, they are find out all possible combination of these 9 transformations, these 9 data dimensions. So how many dimensions are created? 36 dimensions are basically created. Okay. And then they are converting it to its spectral image, which is following discrete Fourier transform. And when they analyzed the spectral image, they found that for different activities, the spectral images are different. So that shows that if you feed that data to CNN, it will be able to classify better, because there is a correlation between the different things. Their intuition was true, correct, and that's why you have this kind of different kind of spectral image for different activity. Okay, so once this is fed to CNN, once this is fed to CNN, then what CNN is outputting? CNN is giving us some probability distribution over the outputs. So that means it is giving us, for example, in this case, yeah, I know I'm running out of time and you are not interested to listen, but please cooperate with me and please tell me, in this case, what is the output? Is it walk? Is it walk upstairs? Is it walk downstairs? Is it sit, stand, or lie? Just by looking at this graph, can you straight away tell me what should be the output? Walking downstairs, walking upstairs, walk, sit, or lie? You can write in the chat box also. What should be the output? Kunal, I will come to your question later. Yeah. Just by looking at this graph, what should be the output? It is saying that there is a possibility 0.3 that the output is the activity was walk. There is a possibility of 0.05 that the activity was walking upstairs. Similarly, these are the different probabilities for the activity. So what do you think? What should be the output of the system? Should it be walk? Should it be walking upstairs? Should it be walking downstairs? Should it be sit? Should it be stand, or lie? Given that these are the different probabilities predicted by the system, what would be your decision? Walking downstairs. Yeah, thank you so much. So walking downstairs is the decision, is the most probable choice, because with 80% probability, the system is predicting that the activity will be walking downstairs. But the other probability, the probability of having any other outcome is almost less than 1%. So it's an obvious choice that the system will output that the activity was walking downstairs by looking at these different probability distributions. But when the probability distributions are different, for example, here you don't have a dominant pattern. The system is saying, the DCNN is saying that there is a 30% chance that the activity is walking downstairs, 29% chance that the activity is walk, 28% chance that the activity is stand. You see that there is no such dominant pattern. For example, here you have a dominant pattern that 80% chance that it's walking downstairs, but only 5% chance. So less than 10% chance for any other activity and 80% chance for one activity. So obviously I will go by this. But here you don't have any such dominant pattern. So for that, the authors have proposed a binary SVM, a bi-class SVM classifier. What is by-class SVM classifier? Now, to resolve between any pair of activity, whether the system will output walk or walking downstairs, what should be the label chosen? Or between walking downstairs and sit, what should be the label chosen by the system? So to decide about this kind of tie, for tiebreaker, you have a pairwise by-class SVM classifier. So now what it is saying, the authors are saying is that maybe there is a 30%, since we are saying that these two activity are very closely matched. Since these two activities, this walking downstairs and walk, these two activities are very closely matched. So they will first take these two activities and feed the data to the SVM. Okay. Now let's say the SVM and feed the data, the feature sets to SVM, and what the SVM is saying that the activity is walk. So then with this, it will start. It's now the other conflict is between walk and stand, because the probability predicted by the DCNN for walk and stand are quite comparable. So we use SVM to resolve between, to break these two, to resolve between these two conflict. And let's say the SVM has predicted it to be walk. So ultimately you say that yes, the system is talking about the decision for the activity, the particular test instance is walk. Okay, so in this way they are using at the final level, they are using this by-class SVM classifier to resolve between the conflicts. Okay, so there are certain challenges of HAR. For example, composite activity, rigorous data collection is of course one challenge. Then composite activity detection is another challenge, because most likely you will not be using, you will not be standing just because you wish to stand. Okay, you are standing because you wish to go and get some tea, because you are tired listening so much of activity, and now while you were inactive probably, so you wish to be active, and that's why you are standing, you are walking, you are getting your tea or coffee, you are coming back and sitting. So that means you don't do one activity, one atomic activity on your own, but you have some purpose for which you do a combination of activities together, and that's why the time interval for each activity will vary. So the composite activity detection is a very interesting problem that people are working on, and how to detect this group of activities or atomic activities like that. And also like detecting concurrent activities requires sophisticated machine learning techniques, because like while answering a call, you may watch TV, while listening to the lecture, you can browse. I don't want you, but probably you can browse something else. So that things you can do. And so this kind of concurrent activity recognition, these are the main challenges of HR, which requires your attention. Well, due to time limit, I will skip this part, but I will very, very quickly go through this application actually, which is student behavior monitoring. So there are things that you can do beyond your accelerometer, beyond your heart rate, and beyond your, what I was talking about, fitness, athletes, and so on and so forth. So what else? You can talk about the mental fitness, the overall kind of activities, the social behavior of individuals using this particular smartphone sensors. Okay, one work is going on at DAIICT, which is Dhirubhai Ambani Institute of Information and Communication Technology, I guess. So it is their paper, their work that I'm I wish to present, because it is one of the very first work that is focusing on Indian students and the social habits of Indian students. And they have collected data for 5 weeks from different students who were staying in campus using a smartphone based application. And as well as that, those students were given with some questionnaires for where they were also asked for example, whether they have, how much they have slept, whether they feel like sleep deprived, how much they were active during the day, and so on and so forth. So what they found, I will just very briefly talk about the major points, but you can, if you are interested, you can get the details from this paper. Okay. So this is the thing. This is the overall activity trend of the 45 students that they got over the day, and they found out, and obviously they have classified activity into simple 2 classes. One is idle, the other one is non-idle. So either the student was idle, that is sitting or lying or so on and so forth, or maybe non-idle mode. So while they mapped this kind of their activity behavior, the duration of their activity trend, then they found that during this kind of 4, 5, 6 day, which was probably the weekends or maybe during the exam times, they found that there was low activity because people were sitting or sleeping, so and so on and so forth. But during the tech fest or sports, the activity levels were, average levels were really high. And in this way, they found the different other trends as well. For example, the sleep trends, the duration of sleep, and so on and so forth, and also many interesting results they got. But another trend that I would like to highlight here is the mobility patterns. So you see, till now we have used the sensors as sensors. That means you have used accelerometer, gyroscope. These things have as sensors. Now you can not only use the sensors for sensing purposes, but you can also use the communication things like communication components, for example, Wi-Fi, as for sensing purpose. How? For example, I know, let's say I know where some access point, like the JUCAC access point or the exact BSS ID of some JUCAC access point. I know where it is fit in the campus. Okay. Now, whenever a device connects to this, or whenever a device sends a probe request, probe request for connection to this particular Wi-Fi access point, I can immediately know that the device was there. The device was in vicinity of that access point. That's why you got this kind of request. So if you analyze the probe requests that you got from different infrastructure access points placed at well-known positions in your department or in your campus, then you can understand the mobility pattern of the users. For example, here they have probably kept in at hostels. Here they were probably, they have moved to many different locations and like that. Okay, so you immediately know their mobility trends, that they were quite mobile and they have visited many places. Many of the infrastructure APs got probe requests from their smartphone devices. Otherwise, like, they don't have. So in this way, using Wi-Fi also, you can have this kind of mobility pattern based recognitions, okay, of activity. So if you expand this particular application, then obviously from a group of students, we can find the mobility pattern of a crowd, of a number of individuals. So that means we can go for crowd activity detection or crowd behavior detection. Once again, crowd behavior you can do with CCTV camera, but with obviously I don't want to repeat all those privacy concerns, pervasiveness importance for CCTV camera versus sensor-based crowd behavior detection. So let's rather go into this kind of Wi-Fi thing. So I will wish to highlight, this particular paper, which is this particular paper. It is a very nice paper, which is on crowd behavior monitoring. So what they did is that they have put Wi-Fi sniffers at as I forgot the exact name of the city, Essen or something. It's in Netherlands, and there was some music festival. And before that music festival, they have actually put this kind of Wi-Fi scanners at well-defined places, okay, around that site of music festival. And what these Wi-Fi scanners are doing, they are just getting the probe requests from the different devices, and obviously that if a device has sent a probe request to this particular device, if a device has first say I was here, so my device has sent a probe request over here, then I have moved in this direction. So this access point would receive a probe request. I would go to this here and it would receive. Now it's not that you actually wish to connect to this Wi-Fi, and that's why you have specifically done something for which your phone will send the request. But it's the thing is that if your phone is connected to Wi-Fi, and if you wish to get internet access using Wi-Fi, then obviously periodically your phone will automatically send this kind of probe request to all the access points in vicinity, will receive that. So in this way they are getting the thing, and in order to avoid these privacy concerns, they are just anonymizing the device identifiers. But in this way you can get the MAC address of the device, that the same device was moving from this place to this place to this place, and in this way you can get the mobility pattern of this crowd. And in this way actually they have found out that this kind of interesting patterns, for example, from where the maximum crowd flow occurred, from which access point to where, and so on and so forth. Okay, so with that I would like to conclude. So to summarize, we have started with smart healthcare. Then we have seen that the purview of human activity recognition does not only remain in smart healthcare, but it can do more than that. And then we have actually talked about the techniques, some of the machine learning techniques and strategies rather, some of the machine learning strategies that you can employ, and some of the deep learning strategies that you can employ for human activity recognition using smartphone sensors and a combination of smartphone and wearable sensors. And finally, we have moved on to this kind of Wi-Fi based activity recognition, or rather Wi-Fi based mobility prediction, mobility pattern prediction works that are going on in the research field right now. So thank you so much. Now to introduce my team, whatever I have said, it has been possible because of my PhD students. Joita has recently submitted her PhD thesis on human activity recognition using smartphone sensors. Priya is working on indoor localization and ION 2, and they are my master students who have also contributed a lot towards this field. So thank you so much for your patient listening, and if there is any questions, please feel free to ask.
Participant, do you have any question? Then you can ask directly, or you can put into the chat box.
Okay, I have one question I guess Kunal Roy has asked, can we ensemble a neural network? Yeah, you can make an ensemble of neural network, but generally you can use neural network as a base classifier for ensemble, but generally we use weak classifiers for designing an ensemble. And you can use even for, if you are using stacking, then you can use this as the second level classifier like that. So should I stop here, or Kunal, do you want me to explain in detail? Okay. Yeah.
So any more question? So since there is no questions, then thank you, Dr. Chandrai Chaudhuri, for your valuable speech. She has discussed many things about the smart home based activity recognition. First, she has discussed about the human activities recognition, gesture recognition, machine learning and deep learning in HAR, and so on. So thank you, Dr. Chandrai, for your valuable speech, and I believe that will
Thank
be
you,
helpful
sir.
to our students and the research community.
Thank you so much, sir. Thank you so much for giving this opportunity.
And thank you so much to the participants for your patience listening this lecture. And tomorrow we are having the two lecture at 11 o'clock to 1 p.m. and the second half from 3 p.m. to 5 p.m. And information that link will be provided by our webinar team, Mr. Prem Kumar. He will communicate everything to your email. Thank you. Okay. And tomorrow speakers are Dr. Amit Chaudhary, is the ex-employee of the CDAC, and another one is Dr. Somiran Chattopadhyay from Jadavpur University. So thank you all. So you can put the feedback form, then close the session.